Oops. Nope. What's the road? Okay. Yeah. You know, I really hate computers. Hate them. When they don't do exactly what I want them to do, I don't like it. There. Now, I feel like I'm pulling teeth to get this thing down. It doesn't want to do this. There. Okay. All right. I want to point out something that I saw on some of the homework, not just in here, but also at the high schools, and that's what I have up here, where we have a series, and there were some people that then looked at the limit of the individual underlying sequence and found that AN goes to 0, and therefore concluded that the series converges. You cannot do that. That's a false conclusion. But you can say if it doesn't go to 0, or if the AN doesn't converge to a set number, maybe it flips around from here to there, then you can say that it diverges. And that's called the test for divergence. But just because it goes to 0, you cannot say that it converges. The prime example of that is the harmonic series 1 over n as n goes from 1 to infinity. This thing we know diverges. But if you just look at the a sub n term, which is 1 over n, and take that limit as n gets bigger and bigger, well, that's going to be 0. But we certainly cannot conclude from that the series converges. So I want to try to eliminate that error in thinking as soon as possible here with this. Okay. All right. Well, we're on section 11.6, and we're talking about 2 more tests to determine whether a series converges or not. And the one we were looking at is called the ratio test. And let me put this up here about the ratio test. Now, the ratio test is good to use if the series contains a factorial or contains a constant to a power. So I want you to keep this in mind, because otherwise, if you don't have some kind of guidelines in your head, you'll just be scrambling to use any kind of test you can think of, and you'll be wasting a lot of time. Now, there are 3 parts to this ratio test. What we look at is the limit of the ratio of, this is the, let's call it the succeeding term over the preceding term, a sub n plus 1 over the a sub n, and we look at the absolute value. So if there are negative things in there, they go away because of the absolute value. And we take this limit as the n's go to infinity. Now, if that limit is equal to a finite number that is less than 1, good news, the series converges by the ratio test. If that limit is equal to a finite number that is bigger than 1 or infinity, I could put also here or infinity, then the series diverges. Unfortunately, we also have the third case where the limit of this ratio is exactly equal to 1. And that's the case where there's no conclusion from this particular test. It's inconclusive. All right. And we did look at some examples here of the using the ratio test, and some of them did involve a little bit of algebra and simplifying things with algebra. So, and dividing by a fraction. Remember, when you divide by a fraction, you have to multiply by the reciprocal of the fraction. Okay. Let's look at the harmonic series here, just for an example of this being inconclusive. Now, we know this thing diverges, n equals 1 to infinity. We know it diverges. The best way to look at this is as a p-series. This is n to the first power, p-series, where p is equal to 1. And if p is less than or equal to 1, it diverges. Okay, so we already know what it does. But let's look at the ratio test with this. Let's just try it and see what it brings. So here our a sub n plus 1 is equal to 1 over n plus 1. We substitute that. And our a sub n is equal to 1 over n. So we're looking at the limit as n goes to infinity of 1 over n plus 1, big line, over 1 over n. Okay, that's the a sub n plus 1 over a n. All right. Since all of this stuff in this particular one is positive, both of those upper and bottom parts are positive, I can certainly get rid of the absolute value sign. So this is going to be equal to the limit as n goes to infinity of the top fraction, 1 over n plus 1, times the reciprocal of the bottom fraction, which is times n over 1. Okay, and so we can certainly look at this if equivalently as just 1 times n is just an n on top, and n plus 1 times 1 just an n plus 1 on the bottom, and then do our little trick by dividing everything by the biggest power of n, and that would be just n to the first power. So we would have here equals limit as n goes to infinity, so that would be n over n for the top part, and the bottom part then would be n over n plus 1 over n, and then those n over n simplify to 1, so that's the limit as n goes to infinity of 1 over 1 plus 1 over n, and we know that the 1 over n term is going to go to 0. What we're left with, though, is a 1 on top and a 1 on the bottom, which means our limit of the ratio is 1. So this test is inconclusive if that were the only thing we could rely on for this particular series, okay? So I want to say this, put this fact down here, which can hopefully help you a lot in determining what, if you have a certain form of your series, what not to use and what to use. So I put big asterisks here to help save you guys time. The ratio test is usually inconclusive for what are called rational polynomials of n. And let me write down a few of what I'm talking about here where it's inconclusive usually. Okay, for example, say we just have a polynomial, I'll just abbreviate it as poly. Say we have a polynomial divided by a polynomial. the ratio test is usually going to be inconclusive there. Or say we have the square root of a polynomial over a polynomial, the ratio test is usually going to be inconclusive there. Or we could have the square root on the bottom, or a polynomial divided by the square root of a polynomial. All right. These are, by the way, these are the a sub n term in this format. Let's see here. Let's get a couple more specific examples. More specific. Let's look. Say we had the summation of n over the square root of n to the third plus 2, as n goes from 1 to infinity. If we tried the ratio test on this, you would end up, after all that good work, coming up to a limit of 1. So this would be inconclusive here. Another example, the summation of 2n plus 1 over, say, 5n squared plus 3, as n goes from 1 to infinity. Again, this is like a polynomial over a polynomial, and you'll find that the ratio test will be inconclusive. This one here is a polynomial. N can be looked at as just a polynomial over the square root of a polynomial. And again, it's going to be inconclusive. So if that is the form, you want to then do something else. In fact, for either one of these, what might you go for either one of these? And we have to start becoming familiar with what test it is we have at our availability. What do we have available here? We have we know what T-series do. We know what geometric series do. We have the alternating series test. What other tests do we have? There's other than the ratio test. There are a couple more that we have. We have the comparison test. And there's one it's similar to the comparison test. The limit comparison test. Right. All right. So now, of course, the comparison test. Oh, and also I forgot the integral test. Oh my goodness, how could I forget that? All right, integral test also. For the integral test, for the last three of these tests, the comparison test, the limit comparison test, and the integral test, the terms have to be positive. All right. Okay. So for these, we could, what I would want to go for with these is use the dominant terms and find a p-series to compare it to. It's for the limit comparison test. Using those dominant terms, say on that one on the right, what would be a p-series that we could compare it to? And that question is also directed to you guys, too. 1 over n, or you could also say 2 over 5n. You know, you could use the numbers there. 2 over 5n. And then that would be a divergent series, right? Because this is divergent. Because it's a harmonic series. And again, I got that by looking at the dominant terms, 2n over 5n squared, and then simplifying them to cancel out an n, and you get 2 over the 5n, all right? And then you you do your limit comparison test with the ratio of this over that, and you end up coming up, I think, with a 1 as your limit, which means the limit comparison test works. We'll look at that again some more, but it's on the homework, and I can't help it. I just get, as soon as I say the word homework. Again, I can't say enough, because if going into the test without having done sufficient homework in that doesn't sound like a real fun experience to me. With this one, now we could use the dominant term would be the n on top, and then what would be the exponent of the 1 on the bottom? Notice we have a square root of an n to the 3 plus 2. Would it just be n to the 3, or would it be something different? Looking at the dominant term. Yes, n to the 3 over 2 power. Because when we do a square root, our bottom number in the in the exponent is a 2. So that simplifies to what? If this is n to the first power, if I subtract 1 from 3 halves, I get 1 over n to the 1/2 power. And so that's also certainly, that's also a divergent p-series. Okay. So for these, where the ratio test isn't going to help me, there is help available, and frequently it's going to be a comparison test or a limit comparison test. All right? Question on first of all, just that little bit right there. Okay, let's go, there's a second test in this section. It's called the root test. In fact, I think here I'm just going to kind of just go with some things here from my written notes. It's similar to the ratio test, except we use roots instead of ratios. So we just look at the a sub n term. We don't do a ratio, and we take the nth root of the absolute value of a sub n, and we, again, take the limit as n goes to infinity. And if that's equal to a number less than 1, it's just like the ratio test, it converges absolutely. All right. Remember what that means to converge absolutely. It means that the summation of the absolute values converge. But what do we know? If it converges absolutely, what else do we know about the series as far as how it converges? Remember that fact from the last time? It converges normally, right. So if we just found that a series converges absolutely, then it also converges normally, okay? All right. And then, again, if we do the limit, the nth root of this absolute value, if that's a number greater than 1 or infinity, then it diverges, just like with the ratio test. And then finally, we've got that last case. When we do the limit of the nth root, if that's exactly equal to 1, the root test is inconclusive. So the 3 cases. Right. All right. What I want to do, and here, might as well just put this down here too. This is a very important, this is another way of directing you to the right test. If your AN term contains an nth power, and we're going to see this in an example, then it could be good to use the root test. And I'll show that in a specific example in just a second. Okay. All right, let's look at, if I can, yeah, I'll make sure we'll see people still writing. And what we're going to look at in the next section is the different circumstances in which we're going to decide to use one test over another. And I know that that personally really helped me when I just reviewed over that again. When I did the 28 homework exercises that you're not going to have all of those to do, but you could always do them if you chose to. It took me absolutely very little time because of the recommendations. I was pretty much able right away to go to the right test to use. And so you save yourself a lot of time. Okay, let's look at a specific example here for this test. So this is a good example of what they mean by an nth power. So example, let's look at the summation from n equals 1 to infinity. Now there's a big parentheses here, and we have 2n plus 3 on top over 3n plus 2 on the bottom, and this whole parentheses is being raised to the nth power. So this is what we mean when we have an nth power. Probably good to use the root test. All right? So let's see here. So our a sub n term is equal to that parentheses 2n plus 3 over 3n plus 2 raised to the nth power. And so when we do the nth root of the absolute value of a sub n, first of all, in this case, do I even have to worry about the absolute value? Remember, the n is going to be 1, 2, 3, 4, etc. None of these are going to be negative values anyway. All right, so the absolute value I don't have to really worry about. This is going to be the nth root of this whole thing, 2 to the n plus 3 over 3n plus 2, but it's raised to the nth power. So the nth root of the nth power cancel each other out. Another way to write this is this. Hold for a big parentheses 2 to the n plus 3 over 3 to the n plus 2. Now the nth power, another way to write the nth root, another way to write the nth root is have the exponent be 1 over n. This is another way to express the nth root, all right? And then this whole thing then is being raised to the n power. Now, when we take a power to a power, we multiply the exponents together. So this whole thing simplifies out to 2n plus 3 over 3n plus 2. All right, the roots and the power cancel each other out. And then we do the limit as n goes to infinity for this. Okay, again, we're going to divide everything by our biggest power of n, which is just n. So this is the limit as n goes to infinity of 2n over n plus 3 over n divided by 3n over n plus 2 over n. All right, just divide everything by that n. And so we get the limit as n approaches infinity. Now that first term is just a 2 plus 3 over n. That's in our numerator. And then the bottom is just 3 plus 2 over n. And then as n gets bigger and bigger, this 3 over n goes to 0, this 2 over n goes to 0. All I'm left with is the 2 on top and the 3 on the bottom. So my limit is 2/3, which is less than 1. So thus, it converges by the root test. Okay. In fact, we can say it converges absolutely by the root test, but since all the terms are positive, it's the same, it just converges in the regular way, all right? And if it converges absolutely, it converges in the regular way. I want to do another example here. If any question with this one here? I want to do one more here with this root test, a little bit trickier than this one, but it's not too bad, I don't think. Again, we have a summation, n goes from 1 to infinity, and our a sub n is this. It's 1 plus 1 over n, close parentheses. Now this time the power is n squared. Okay. Again, we have a n power, so I think we want to try the root test. So a sub n is equal to that 1 plus 1 over n to the n squared power. And so the nth root of a sub n, I guess I don't really need to worry about the parentheses here, the absolute value, again, because everything here, this is n from 1 to infinity. Everything's positive, so I don't have to worry about the absolute value. What does this equal? This is 1 plus 1 over n raised to the n squared power. That's our a sub n. But now, let me put even a bigger parentheses around it. I'm raising that to the 1 over n power. That is the nth root. Is everybody okay with that? 1 over n as another exponent there when you're taking the nth root. All right, let's multiply the exponents together. So this is 1 plus 1 over n. And now let's multiply those two together. So we have n squared times 1 over n. That gives us n as a result. So my new exponent here is n. So that's my nth root of a sub n. And then, what we need to do then is take the limit as n goes to infinity of a sub n. So that's the the nth root of a sub n. So in this case, that's the limit as n goes to infinity of 1 plus 1 over n raised to the n power. Now, this right here, I think I mentioned it before. Acacia's nodding her head. She knows what it is. It's equal to e. This limit of 1 plus 1 over n, as we take the whole thing to the nth power, is equal to e. And you can verify that through the L'Hopital's rule using the 1 to infinity case using that rule. The function you would use would be 1 plus 1 over x instead of 1 over n, close parentheses, raised to the x power. And you do that 1 to infinity case. Okay. All right, and I think I had told you guys you need to remember that particular limit. It's always good to know. So therefore, what do we have here? The limit is equal to e, but e is approximately, what, 2.72 or 2.718. So e is greater than 1, so therefore it diverges. Since limit is bigger than 1, it diverges by the root test. Okay. Now here's another thing that, as far as something that's helpful, if the ratio test is going to be inconclusive, then the root test is also going to be inconclusive. And vice versa. If the root test is inconclusive, in other words, the limit is equal to 1, then the ratio test will also be inconclusive. So I want you to remember that. So let me put this down here. If the ratio test is inconclusive, and that means, i.e., the limit is exactly equal to 1, then the root test is inconclusive. and vice versa. Okay, also the other way around. So we know that the ratio test usually doesn't work if we have a polynomial over a polynomial. Well, the root test isn't going to work for that either, okay? Because if one doesn't work, the other one ain't going to work either. Okay, so that ends this section here, 11.6. And so what we're going into in the next section, and I've got a PDF file here that I've also put onto Blackboard. You can print it out for yourself. I didn't make copies of it for you guys here today, but I do maybe I will do that. What we're looking at here in this next section is strategy. Just like we had integration strategies where we try to identify a form so we knew what we could do to integrate, we have a similar kind of strategy with series. So this section 11.7 is a strategy for testing series. All right, let me get this thing. Yeah, here we go. All right. Okay. And let me just put here, this PDF is available. Oops, never can type. Okay, so thing is, as I had just said, the main strategy is to classify the series according to what its form is, all right? So, first of all, is it a p-series? So is it something like 1 over n to the p power, where p is a constant? Then if it's a p-series, we know that it's convergent as long as the p is greater than 1, and it's divergent if the p is less than or equal to 1. So we know how p-series behave. All right. So remember with the p-series, the n varies, but the exponent stays the same. Right. Now, it may be a geometric series. Okay, that's where everything keeps getting multiplied by that common ratio. And if it's a geometric series, then we know that it converges if the absolute value of the common ratio is less than 1, and it diverges if the absolute value of the common ratio is greater than or equal to 1. Okay, so we know how geometric series work. And these two are really kind of the backbone of what we use for comparing things with, because we know how these things behave. Okay. Now, if the series has a form that is similar to a p-series or to a geometric series, then the best thing to use is, and we have done an example of this before, then we use either the comparison test or the limit comparison test. All right? And that's the kind of thing that I was talking about where, oops, sorry about that. Nelson, I might need your help here. let's see, this might not work here with this one. On top? Let's see, I wonder if that'll do it. Right here? Yeah, this thing doesn't want to, this is the thing I was fighting with earlier. It doesn't want to move. No. Let me make it smaller. And blast. Okay. Okay, there's a little part of it over here. There we go. What I'm talking about here is, again, if we have, n squared over square root of n to the fifth plus 2n, this type of thing, this is actually similar to a p-series. It's like a p-series, and that's where we look at the dominant terms. In this case, the top term, well, there's only one top term, that's n squared, and the bottom term then is, I need to make this bigger. This is not going to work out. Let's make the bigger one n to the 15th power. Let's do something like that. So my bottom term then, my dominant term is n to the 15th over 2 power. And so then I can simplify things by using the rule of law of exponents. And 15 over 2 minus 4 over 2, or 2, gives me n to the 11th over 2 power. So this, of course, is very much a convergent, this is similar to a convergent p-series, where we look at the dominant terms. So that's this is the kind of thing I'm talking about when I say it's similar to a p-series. All right. Now, similar to a geometric series, I'm hard-pressed to say, well, maybe it could be something like this. Okay, that's actually similar to two geometric series, and they both converge because here r is equal to 1/3, r is equal to 1/7, so they both converge. All right, so, and then if you have the case where it's similar, then you want to use, I like to use the limit comparison test, but you could also use the comparison test. Remember, the comparison test is you have to have it has to be less than the other term. So for the comparison test, say we have two sequences, two series, A sub n summation, B sub n summation, and say we know that this one converges. Say it's a p-series or something like that. We know it converges. To do the comparison test then, and these have to all be positive, by the way, positive in value. To do the comparison test, if we want to show that this one converges, we need to have that A sub n is less than B sub n. And then if A sub n is less than B sub n, and the B sub n converges, then we can say the A sub n converges. All right, that's the comparison test. And then also, if the B sub n diverges, if the summation of B sub n diverges, if we're able to show that the A sub n's are bigger than that, then we can say the A sub n's also diverge, all right, by comparison. All right, now the thing is, getting back here to this slide, these comparison tests only apply to positive terms, okay? So guess if we have something that isn't always positive, we can look at the absolute values, and that makes them positive. And so if we look at absolute values, so we can apply the comparison test to the summation of the absolute values, and then test for absolute convergence. And if it converges absolutely, it converges in the regular way. Okay, and here I've got an idea, again, what similar to a p-series means. It's a polynomial over a polynomial, or a radical over a radical, or some combination. And we have to look at the dominant term in the numerator and in the denominator for the limit comparison test. Okay, continuing with these strategies. Now, if we have a series like this, -1 to the n, or n minus 1 times a positive term, then they're alternating between positive and negative. The obvious thing you want to go for first is the alternating series test, all right? That's what you want to go for as your first choice. Now, another possibility is this. Say your A sub n is equal to something that, hey, you look like, boy, I think I can take an antiderivative of this thing. Now, it has to be positive and decreasing in value, but you may then want to go for the interval test here. One example that comes to mind is 1 over n times the ln of n, as n goes from 1 to infinity. Basically, we could say, wait a minute, you know, I know that the derivative of the natural log is 1 over x. So maybe and this is a decreasing, it keeps getting smaller because the denominator gets bigger. It's positive in value. Let's look at the corresponding 1 over x times the ln of x, as x goes from, let's say 2 to, 1 is okay, 1 to infinity, and use u substitution to evaluate it, okay? We would want to have u equal the natural log of x, so du is 1 over x dx, and go from there. Because it looks like, let me put this up higher, because it looks like, hey, this could be an antiderivative that I could readily get, all right? And then you always want to keep in mind this test for divergence. If you're able to just look at this thing and see that the A sub n term, the limit, doesn't go to 0, that right away is, as I mentioned at the beginning of class, can tell you this thing is going to diverge. And it's the test, that's the test for divergence. So sometimes you're able to eyeball that quickly. Now, what I think I will print this. I know I see some people fast and furiously writing. I will have this printed out for you guys on Wednesday, okay? Series that, and I mentioned this previously, series that involve factorials or a constant raised to a power, the nth power, usually are going to work with the ratio test. But notice right underneath there I say the ratio test should not be used for series that have the form polynomial over polynomial, or radical of a polynomial over a radical polynomial, or some combination of the two. It's not going to get you anywhere. And then finally, if our A sub n is an nth power of something, here it's of the form b sub n raised to the nth power, then the root test may be useful. And we did a couple of examples of that just a few minutes ago. So you can see it all depends on the form of the series, what you want to go for. And the only way this works in practice is to practice on the homework. All right. Finally here I have a couple of useful facts, and these are all things that I would, if I had already done it, I would put an asterisk by. There's no reason that you have to reinvent the wheel for some of these facts, okay? Just know that they're true. Limit of n raised to the 1 over n power as n goes to infinity, which is the same as the limit of the nth root of n as n goes to infinity. The fact is that equals 1. You can prove it using L'Hopital's rule, but that's what it equals. It equals 1. Similarly, if we just have a constant c that doesn't change, a positive constant c, and do the limit of the nth root of that, that is also going to equal 1. Another very helpful fact is this, is that the natural log of some number n is going to be less than the number itself. Natural log increases very, very slowly. The number itself is going to be larger than that. So this is a very useful fact to keep in mind, that the natural log of a whole number is going to be less than the whole number. Okay? Finally, just to know that e is equal to 2.718 is also a good thing to remember. And then this we just saw a few minutes ago, this limit of 1 plus 1 over n raised to the nth power, that's equal to e. All right? So, what we're going to then look at, well, we've got a couple more minutes left. I'll get this printed out. What we're going to then do for the rest of this section is we're going to look at several different types of series, identify which one of these rules would apply to it, all right, and then look whether it's convergent or divergent, all right. So we're going to have different types of things that we can use various different tests for, and so instead of scrambling around trying to test everything, we really don't have to. So I've got basically 9 examples that we'll go through, okay? So I guess we'll no use starting that now. So that's what we'll start on Wednesday then. Thanks. Guys, I'll send and it can be copied. All right, so that's a handout. Yes, sir.
I notice how you're like trying to keep so close to the side. The camera actually comes all the way to the edge of this, so you actually have a lot more paper to write with.
Oh,
Like if you go to that half and half thing again.
let's see. First of all, let me stop recording so that stops. Oh, wait a minute. What did why did it suddenly say I'm recording? I wonder if all this, I probably blew the recording.